CicuDevices. Impella, Chapter 1, Physics and Physiology. Part 1. The Impella device is a miniaturized mechanical circulatory support. It is a catheter-based micro-axial flow pump that can be placed percutaneously or by surgical cut down into the femoral or subclavian artery. Impella has become a common mechanical assist device used in medical and surgical cardiac intensive care units, mainly to support percutaneous coronary intervention and to manage cardiogenic shock. Next, we are going to review the physical principles that explain the operation of the Impella catheter. The Impella pump is a miniaturized axial pump. It operates in continuous rotation, where the blades generate suction at one end and positive pressure at the other end. So, if we add a tube, we can transmit the suction to the inlet and ejection to the outlet. This way, the flow will follow the generated pressure gradient. Finally, we would only need to add a grid at the inlet and a blunt tip, both to prevent damaging cardiac structures. We would then have a very basic Impella. Impella device is a microaxial pump, so the flow it generates follows the principles of such machines. Flow in axial pumps depends on various factors: rotation speed, impeller diameter, impeller design, fluid viscosity, height at which the liquid is being pumped, and, in the case of ventricular assist, the pressure difference between cavities. In this way, if the catheter and patient remain constant, we can consider that the obtained flow depends mainly on the pressure difference between the inlet and outlet. If the pressure difference is low between inlet and outlet, then the flow is high and the power or current used to displace this amount of liquid will also be high. On the contrary, if the pressure difference between the inlet and outlet is high, the flow will be low, and the required power will be low too. In these graphs, we can observe the relationship between current and flow, and between pressure difference and flow for a specific rotational speed, or P level. When positioned correctly, the impeller operates between two chambers with dynamic pressure based on cardiac cycle. Therefore, in a catheter placed between the LV and AO, pressure difference is highest during diastole, requiring less current and resulting in lower flow. Conversely, during systole, the pressure difference is minimal, producing greater flow and consuming more current. In this way, during the cardiac cycle, there will be a sinusoidal pattern in both current and flow. Once this is known, it's not difficult to understand the current curve on the Impella console screen. It also helps to comprehend the minimum, maximum, and average flow figures that the console displays. The axial pump mechanism of the Impella is not completely isolated from the bloodstream. This would result in some blood flow entering the system. If the blood comes into contact with the mechanism or the engine, it begins to form a clot that would progress to impede the functioning of the system. So, the device's design incorporates a purging system consisting of a constant flow of liquid at a preset pressure. The physics of this matter is the same that compels us to place a pressurized intravenous solution in an arterial line to prevent blood backflow. In this way, the perfused purge flow at a pressure above the blood pressure at the aortic root prevents the entry of blood into the mechanism and the formation of clots. The Impella device can determine pressure in real time using optical fiber and laser. This is called an optical pressure sensor. System emits a pulse of laser towards a reflective diaphragm and measures the time it takes light to return. Knowing speed of light, device calculates the distance with great precision, in the range of micrometers. A laser emitter generates the laser pulse, which travels through the optical fiber and is reflected on the surface of the diaphragm acting as a mirror. The laser returns to the receiver or sensor, where the elapsed time is measured, allowing for the calculation of the distance traveled. In the following animation, we can observe the phenomenon in motion. We could consider this equilibrium position as zero pressure. If pressure is applied to the diaphragm, the distance traveled decreases proportionally to the exerted pressure. This small variation can be detected with great precision by laser. An algorithm correlates the difference in distance with the pressure received by the diaphragm. This system is integrated into the catheter and allows for establishing real-time, highly reliable blood pressure. To be continued. If you've enjoyed our video, please press the like button and subscribe to support us so we can continue creating quality content like this.